Hi everyone. In an earlier video, I mentioned that antidifferentiation of partial fractions requires us to consider inverse exponential and trigonometric functions. And now that we've covered exponentials and logarithms, let's start the discussion about the trigonometric case. Let's start by reminding ourselves of some things that you should have already learned about trig integrals, starting with these integrals of sine and cosine, which you've definitely seen before. In addition to these, you should also be aware of the integral of secant squared. After all, this integral represents a function whose derivative is secant squared of u. Which function would that be? I hope you were able to answer tan of u based on your knowledge of derivatives. And what about the integral of cosecant squared? Well, given that the integral of secant squared is tan, you might reasonably guess that the integral of cosecant squared is cotan, and you'd be right, except there's also a negative here. Next up, what is a function whose derivative is secant u tan of u? You should also know the answer to this one. That would be secant of u. And once we know the integral of secant of u tan of u, then we probably also know the integral of cosecant u cotan u. Well, given that the integral of secant tan is secant, you could guess that the integral of cosecant cotan is cosecant, with a negative. I hope you're starting to see a pattern here. The integrals of the cofunctions are always exactly what you think they'll be, but with an extra negative attached. So as long as you know the integrals in the left column, then you can come up with the integrals in the right column pretty easily. Now, if we know the integral of sine and cosine, then we also ought to know the integral of tan. But I'm guessing not everyone watching knows this formula, so we'll talk about that in this video. And the same goes for the integral of secant of u. And of course, once we know the integrals of tan and secant, we can also predict the integral of cotan and cosecant. So our goal for the remainder of this video is going to be to fill in these 4 question marks. Let's start with the integral of tan of u. It turns out this is the natural log of the absolute value of secant u. The fact that this formula involves secant should come as no surprise, since there always seems to be a relationship between secant and tan when it comes to derivatives and antiderivatives. And that's something I always like to keep in mind just to help myself remember all these formulas. So where does this formula come from? Let's actually prove this. The first thing to do is recognize that tan can be expressed as sine over cosine. Expressing something as a fraction isn't normally advantageous when it comes to taking an integral, unless that fraction happens to be of the form f prime over f, and what we've got here is pretty close to that form. But actually, the derivative of cosine is negative sine, so this integral isn't quite what we wish we had, but on the other hand, if we want the numerator to have this negative, we can always make that happen as long as we cancel it out with another negative. So in doing that, I really am dealing with the same integral, but I've truly expressed it as f prime over f. And as discussed in a previous video, that always results in the natural log of the denominator with an absolute value. At this stage, you're done taking this integral, but you'll notice that the formula we came up with isn't quite what I said it should be at the top of the screen. So there is one additional step required here, and that is to use a property of logarithms to bring the negative up as an exponent of cosine. We know that a -1 exponent indicates the act of taking a reciprocal, and we know the reciprocal of cosine is what we call secant. And so with that, we do get the formula that I claimed, which completes the proof. Next up is the integral of secant of u. It turns out that's ln of the absolute value of secant u plus tan u. Here again, we see a relationship between secant and tan, so at least in that sense, this integral formula is not surprising, and again, we can use that to help us remember the formula. So why is this formula true? Let's prove it. Unfortunately, unlike the tan integral, this is not of the form f prime over f, at least not as it's currently written. However, we can force it to have that form if we multiply and divide by secant u plus tan u. That probably looks incredibly random, but for the moment just trust that this will get the job done, and notice that by multiplying and dividing by the same quantity, I haven't technically changed the function I'm dealing with, so this is at least a valid step even if you don't see why it's useful yet. Next, I'm going to expand out the numerator by applying this secant of u to each of those terms, which gives me the result that you see now. And after that, you'll notice that this is literally of the form f prime over f. Pause now and verify for yourself that the numerator is the derivative of the denominator. And once you're convinced of that, we know this evaluates to the natural log of the denominator with an absolute value, just like every other f prime over f integral. So here we see the formula I claimed at the top of the screen, which completes the proof. And with that, we're ready to fill in these remaining four formulas. We just found the integral of tan of u is ln secant of u. So you could expect the integral of cotan u is ln cosecant u with a negative, and that's exactly what it is. Similarly, we just saw the integral of secant u is ln secant u plus tan u. So I'd expect the integral of cosecant u is ln cosecant u plus cotan u with a negative. I should say that's what I expect, but just because it's what I expect doesn't necessarily mean that it's true. But a more convincing argument, if you want, can be made using the same ideas I used when proving the integral formula for secant just now. So I suggest trying to form a proof of this last one for yourself, if you like. So with all of this, though, we've accomplished our goals for this video. Make sure to put all 10 of these on your formula sheet for future reference, and we'll continue this conversation in the next video.